Hi, my name is Ritam Sen. I'm from San Diego, California, and today I'm going to talk to you about my project, an in-situ CubeSat mission for detecting, tracking, and mitigating small orbital debris via sensor fusion and laser ablation. Small space debris sized 1 to 10 centimeter in diameter, is largely untracked by ground-based radar. However, it can cause mission-ending damage. The European Space Agency estimates that 1.2 million of these fragments orbit around Earth. Without intervention, continuous cascading collisions trigger the Kessler syndrome, rendering critical orbital bands permanently unusable. The problem is no longer theoretical. In November 2025, Shenzhou 20 was hit with a piece of untracked space debris. A Russian satellite was completely fragmented into thousands of pieces this January, among other recent events. The core approach fuses a solid-state flash lidar and a global shutter camera, specifically because radar wavelengths are fundamentally too long to resolve centimeter-scale targets. Extended Kalman filter fuses both sensor streams into a real-time state vector, while a YOLO V11 model trained on 20,000 synthetic images handles debris identification. From there, the project continues with hardware fabrication, as you see here, observational testing, and physics simulation. The mission design architects 300 CubeSats placed in 20 constellations of 15 CubeSats each along the 750 to 1,000 kilometer altitude band. Each of these CubeSats employ a Earth tangent pointing geometry, creating an omnidirectional detection disk. The 5 benchmark tests achieved a 94.4% state vector reconstruction accuracy. Mitigation pointing accuracy also received 97.3% under nominal conditions. Stress testing established a 5 to 7 millimeter detection floor, and robustness through different speed and light stress conditions. Mission scale simulations, 300 CubeSats, 450,000 debris objects, and 500 trials yielded over 290,000 debris detections, over 250,000 debris tracks, and just around 130,000 mitigations over a 1-year simulation period, with orbital lifetimes reduced up to 78.9 times. Jacobian analysis confirms 1.36 meters of positional uncertainty at 10 kilometers, over 1,000 times better than current existing ground-based radar infrastructure. Lab-to-orbital scaling is physically validated. Point density scales predictably with range, and lab dwell times are the conservative bound for actual orbital dwell times. This research confirms a physically feasible, first-of-its-kind closed-loop architecture for detecting, tracking, and mitigating small orbital debris. For more in-depth information about my project, please refer to either my project slide deck, my project notebook, which is linked on the slide deck, or my project photo book, also linked on the slide deck. Thank you for your time, and I hope to see you at this year's CSEF.